Okay. First of all, thanks for the organizers for inviting me to this very interesting workshop. I'm going to talk a little bit about results and forecasts using spectroscopic surveys, particularly BOS, and few words about what the DESI survey may be able to do in the near future. Okay, as very likely all the audience is aware, because of the precision observations that we have currently, now we have a quite complex or more interesting picture of the universe. Recently, the EVO surveys tested this acceleration at 11 sigma significance. So we are in an accelerating universe. One possible explanation is the dark energy. So constraining the equation of state is one of the goals of EVOS and many of the surveys. There is also the possibility of having a cosmological constant, which is the standard Lambda-CDM model. But also there are alternatives. There could be a dynamical field, and there could be also a modified gravity, which is related to what we would like to discuss today. So the evolution of the distribution of matter in the universe is a powerful constraint. We can derive important parameters. I already mentioned the physics of dark energy, but also constraints on neutrino mass, perhaps inflation, and also, as I mentioned, gravity. Particularly for the EVOS, and it applies also to DESI, we have three different kinds of tracers, which are large red galaxies, emission line galaxies, and quasars. And also we have a absorption of quasar emission, and we can use the Lyman alpha force to have constraints, a larger redshift. This is an image of the Sloan telescope and the footprint of the different tracers. We can see, particularly we have luminous red galaxies in redshift between 0.6 and 1, emission line galaxies between 0.6 and 1.1, and quasars between 0.8 and 2.2, and Lyman alpha 4 is redshift larger than 2. We can do a quick comparison between BOS and EVOS. Essentially, the purpose of EVOS was we can see the color section which has some overlap with the green and red squares in the left-hand side image. We can see that the new observations are filling a gap between the Lyman alpha observations in BOS and the color regions. And we have the regions also with Lyman alpha with a higher density observed points. An important thing for doing cosmology with this kind of surveys is the baryon acoustic oscillation, which is a result of having baryons falling in the gravitational potential wealth of dark matter. There is a competition which oscillates at the speed of sound at the moment of recombination. And this last oscillation is imprinted in the matter distribution and also in the distribution of galaxies. And we can see here on the right-hand side a plot of the correlation function, and we can see the detection of the BAO peak. This BAO peak is related with the acoustic horizon that I was mentioning before. Okay, then this last oscillation is imprinted in the distribution of matter and also in the distribution of galaxies. One quantitative way to study is using the 2-point statistics, particularly the correlation function or the power spectrum. If we could measure the correlation function along the line of sight and also projected in the sky, because of the isotropy, we would get these circular contours of correlation function. However, the observations use redshift in order to make this survey and the map of the tracers, which are the galaxies that I mentioned before. And this is what we are obtaining. There are different sources for this lack of symmetry. One of them is because we measure redshift with potentially measure the Hubble flow. However, they are also sensitive, this redshift, to the peculiar velocities. Also, because once we have the observations and if we presumably corrected for all possible systematics, there is also the possibility that we are trying to fit the observations with a model, for example, which parameters are slightly different to the true answer. Then, because the distance along the line of sight is sensitive to the Hubble parameter, and the one across projected on the sky is sensitive to the angular size distance, they have different dependence with the redshift. And if for some reason we assume a fiducial model which is not corresponding to the true model, we're going to have because this different dependence with the redshift, we're going to have this circular symmetry is going to be broken. And this is the well-known Alcock-Pashinsky effect. Then this should be considered at the moment of making interpretation of those contours of correlation function. We also have physical or dynamical process that can break this circular symmetry. This is the redshift space distortion. We see this diagram. In the linear regime, it produces a flattening of this contour. If for some reason we get the moment of the turnaround, all the redshift will be compensated and we will get the result in the middle panel. And once we are in the non-linear regime, we have the well-known fingers of God effect, which is this vertical elongation. Typically, the last one is happening at smaller scales, and at larger scales is possible to observe this flattening. Now, how can we connect this flattening with the growth of a structure and also afterwards with the observations? We can see the linear perturbation equation for a fluctuation. It has the general solution that is in the lower panel. And this D is what is called the linear growth function, particularly the logarithmic derivative of that quantity. In general, this growth factor is dependent on the cosmological model. It has the value of 0.6 for standard CDM. For lambda CDM is 0.55. For different dark energy models is like that. And for example, for one alternative gravity model, the DGP is, for example, 0.68. So one possible avenue for testing this is accurate estimations for this growth factor. We can see that, for example, if we apply this continuity equation, we can actually connect this growth factor with the peculiar velocities. However, at this moment, we are going to focus more on measuring that with the deformations in the correlation function contours. We can, this is a linear perturbative analysis. From the perturbation, we can see that it's possible to estimate the power spectrum. Also, we can see that we are not really measuring the fluctuations or the power spectrum or the correlation function for the density field. We are actually, we have tracers, which are, for instance, the LRGs galaxies, ELGs, or quasars, for example. Then we can see that the perturbation or the statistics, the 2-point statistics for our tracer is related to the matter density field perturbation through the bias parameter and the grow function parameter, and also it has a dependence to the direction on the sky, the line of sight. If we combine this in the power spectrum expression, we can see that we are actually analyzing those contours of correlation function. We are estimating the growth factor times sigma A or the bias times sigma A. However, we can use strategies to break the degeneracy and estimate any of them. For example, one possibility is if we use moments, for example, if we use a Lejeune polynomial expansion for the power spectrum or the correlation function, the monopole and the quadrupole, or, both of them, they have the bias dependence and the growth factor dependence, and we can potentially measure the left-hand side. Then, in principle, it could be possible to break degeneracy, even more if we have multiple tracers, like in our case. However, we need to control all the systematics. When we talk about high accuracy, that means the previous discussion was just to illustrate in a simple case what is the strategy. However, if we would like to go to high accuracy, typically we need to go even before linear analysis or linear perturbation theory. Then there is a full community doing this kind of analysis, and some of them generate templates which are directly compared with the observations, and typically people optimize and find the best fit based on some of those templates. People working on perturbation theories have produced different ones. As accuracy improves, the small details on those templates based on perturbation theories is more important. Those templates and results of perturbation theories, they have a very powerful synthetic capabilities, because if we understand the physics of them and they are capturing all the nonlinear behavior, it's possible to build, for example, accurate and physical motivated mocks in order to make an interpretation of observations. However, they typically work in a team effort with the N-body simulations also, because typically capturing the nonlinear evolution, particularly when we introduce an extra field like some alternative dark energy models or some alternative gravity models also, those physical effects are typically in the quasi-linear or non-linear regime. Then it's important to have a mutual feedback between perturbation analysis and embodied simulations. Those embodied simulations typically are useful for capturing the nonlinear behavior, which is a very difficult task, and also to analyze and correct for systematics, starting from cosmic variance, different biases, also analyzing those simulations have some possible artificial biases that should be controlled, that typically in low accuracy observations, they were not important, but as accuracy is increasing, they start to be important in the same way as templates. The details of HOD, I'm going to explain very quickly what is the HOD, even initial conditions for the simulations. They are expensive, and this is even more critical for the modified gravity case. I'm going to say a few words more about simulations in the next slides. Also, there are other systematics like fiber collisions, which constrain our ability for the clustering at the small scales. Particularly, they are important for the mission line galaxies, and there is people working in models in order to accurately correct for these effects, and typically those strategies are tested also against simulations. For the case of EVOS, but it's the same also for DESI, there are like two big branches for using the simulations. Some of them are high accuracy or fidelity mocks. That means very high resolution simulations that they have a volume comparable with surveys, and also they control noise in the modes, for example, the VAO modes or RSDs. Also, they allow to study the statistics of the tracer or the estimator that we would like to analyze with very high accuracy. However, typically those simulations are very expensive to be produced. I'm giving some examples. I will give more detail in the next slide. And also, there is also the strategy of having approximated mocks. I'm mentioning here two cases. I'm going to give more details for the easy mocks. The GLAM or QPM typically are homogeneous grid, Eulerian grid, which are very optimized. In some cases with a time step, in some other cases with the accuracy of the simulations, in order to have a fast production of the main density field, and on top of that, being able to produce realizations with the same statistical properties of the tracers, and correct for things like cosmic variance and other things. Okay, each kind of approach has different purposes. I already mentioned that in words. I'm presenting few information there also. I would like to emphasize the importance of HPC for this kind of the process of the analysis. In some cases, is comparable, particularly when we are going to high accuracy, to the quality of observations and also the more theoretical models. Being able to produce accurate models is very expensive and is a big part of the interpretation process. All particularly the effort in EVOS, and also is the same happening in DESI, obtain a lot of benefit from NERSC, particularly using the Cori supercomputer. And locally here in Mexico at UNAM, also we contributed with a small piece analyzing LRGs, and also we are working producing fast mocks for DESI MG forecast. I'm going to mention very little bit about that later. One of the large simulations is this outer ring embodied simulation, which is a 3 gigaparsec box size with a 10 to the 12 particles. At the moment when that was run, it was run in the #1 computer in the top 500 list in the world. It is a very expensive effort, but it's very useful because relaxes a lot of assumptions that people use before related with noise, related with how representative was using a small box compared with the volume size of the actual survey. On top of that, people typically define mappings between dark matter halos and the statistical properties of tracer galaxies, either LRGs or ELGs or quasars, for example. We might believe that this is a small detail. However, if we would like to go, if the signal is at a very high accuracy, for example, inside few percent or 1%, all the details about how HFD is performed is important. If we use luminosity function, stellar mass function, star formation rate, colors, Vmax, the differences are small, but have a significant impact if we are hoping to get few percent accuracy. This is an example of those EasyMux. EasyMux essentially is a code that is the evolution is performed using Seldovich approximation and is evolving the density field, and is using the fact that with other particle simulations, they quantify the PDF of halos in different regions of the density field, and then once evolving the density field is quite cheaper than the previous simulations, then once the density field is evolved and is captured with good enough accuracy, then there is a sampling of the density field in halos based on a previous simulation. This is making cheap the process, however, is linked to the simulation that was to the estimation of PDF. For example, if I would like to have an alternative model, I need to have a full previous simulation in order to apply this strategy. Then this was used for, this one of the approximated methods used particularly for allergies in EBOS simulations, and they were very important to control all the systematics. Then using those high accuracy and also the fast simulations, people were able to explore the different possible systematics. And this is a listing of the systematics for the growth factor using different tracers. Particularly, they are below compared with the statistical sampling error. I should mention that all of them was made assuming lambda CDM. If we would like to apply this with very high accuracy for an alternative model, we need to have these fast mocks also for alternative gravity, for example. Then before the EBOS, that was the situation for the growth rate of a structure at different redshift. We have the main general sample of Sloan and other surveys, BOS also. Then with EBOS, we obtain more points at redshift 0.7, 0.85, and 1.84, particularly for quasars. It's possible to go further in redshift. There are like two flavors for analyzing these quasars, estimation for the growth factor. We can combine all of them center in 1.48, but also we can use what some people call tomographic approach, which is essentially a binning. Then we can have more points. I'm going to show some of the discussion in a few slides ahead. Okay, then once we include EBOS, we are in position to try to constrain this growth factor, for example, for alternative dark energy models and also for gravity. This is the continuous black line is lambda CDM. The other lines are for different values for equation of states. And recently, there was the final announce for the results of this EBOS collaboration. Essentially, what is concerned with the growth factor and possible constraints for gravity. In blue, well, first of all, we have this particular parametrization for alternative gravity, where one of them is mu is proportional to the effective gravitational constant. The other sigma is related with the slip, gravitational slip. Then we have now this figure to the left, where is a diagram where those parameters are constrained using the blue contours are using the RSD estimations for EBOS at the 65% and 95% significance. In red, we have a weak lensing and also CMB lensing. And the gray is the combined optimization for those parameters. We can see that the general result is that the gray, more significant contour is centered around or very close to mu0 and sigma0, which is essentially lambda CDM or general relativity in this case. There is also a recent effort combining both EBOS results and latest data of different tracers, including lensing, including supernova. Then these are the results that they obtained. Again, they perform different strategies for the optimization. The simpler one was estimating the index, the parameterization of the growth factor using the matter density. Then taking this, this is the figure to the right-hand side. The dash line, horizontal dash line is the one corresponding to lambda CDM. We can see that data are different. And again, the brighter color is related with a more significant test, and the dimer color contour is related with a 65%. Then we can see that data is, and in this case, they use for the RSD, the tomographic strategy, the binning, instead of using only a single redshift for the tracer. In this case, there is, even that it is consistent with the general relativity, there is some indication that maybe some signal of modification of gravity. However, this is at the level of 3 sigma. The same we can see to the left-hand side if instead of giving a particular model for the effective gravitational constant or the slip, we have an expansion like the one which is in the small square to the right-hand side. And there is some low significance possible signal. However, still the systematic have to be analyzed. In general, it's consistent with the general relativity. However, using this tomographic strategy, there seems to be some signal. This is opening the road for example, DESI, more accurate observations, better statistics, and all these kind of analysis could be done again.
Pardon, Octavio, we have 5 minutes left.
Okay.
Thank you.
Okay, just very quickly, well, I just mentioned DESI. The survey already started. This is in general, we are going to have the same tracers as EVOS. Actually, the ELGs in EVOS, they open, they were very helpful to understand and to systematics and how the design of the DESI survey. In this case, there are like several, almost more than an order of magnitude more tracers. Then the statistical uncertainties are quite lower. We are in the process of trying to quantify, to make the forecasting, either with simulations, analyze convergence. Particularly, we have been working also only with the FOR and DGP. Also trying to estimate how good are different estimators, which are the systematics. For example, for H of D, which is the effect of if we use a stellar mass or other quantities for making the H of D. Some people have been, particularly here in Mexico, they have been exploring using high order statistics like 3 points. Other people have explored Minkowski functionals, voids, phase space. This is estimation of the multiples of correlation function based on the simulations. In the right-hand side, also there are the mass function of halos, mass function of galaxies. This is a test about the effect of, the question was, the uncertainty about doing H of D, how that competes with the signal of different models of gravity. For this particular case, apparently, including this statistic, this uncertainty for stellar mass, is still possible to recover difference between GR and FOR. This is using 3-point correlation function, which that Gustavo Nis, Alejandro Avilés, and Zachary Slepian are leading. Particularly, there seems to be some signal. However, still the noise, the significance of this signal is still being evaluated. Also, the possibility of using truly peculiar velocities could be, even that DESI was not designed to be a peculiar velocity survey, could be interesting. And I think I don't have more time. Then in general, EVOS extended test for gravity beyond 0.8. And we are on the road of in DESI trying to understand systematics and maybe breaking degeneracy. Thank you.
Okay, thank you very much, Octavio, for your nice talk. We open the session for questions. If anyone wants to make some inquiry to Octavio. Okay, I have one question, Octavio, if that's possible. I think that I am going to give the word to Jorge. Is that okay, Jorge?
Yes, thank you. Thank you for your talk, Octavio. You haven't mentioned neutrino. Do you think, apart from the break in the power spectrum of the neutrino signal, can we find something else about the signatures the neutrino can provoke in the structure formation?
Yeah, there could be actually some degeneracy. I was wondering to include it or not, but definitely there could be degeneracy. If one, well, you know that is one of the things that we're trying to quantify also. And but we have the hope, as you know, that including more estimators, the combination of different estimators and tracers, we may be able to break some of the degeneracy. Particularly, I was mentioning voids in one of the things that have been explored. So maybe using them is possible to break such degeneracy, but we will see.
Okay, thank you.
Okay, thank you, Jorge. Well, my question was the same that if I have the same doubt about the neutrinos. Well, thank you for Jorge to point it out. So I think there is not more questions. Okay, Octavio, thank you very much for your talk. We are going to move on to our last seminar of today after the panel discussion. So Jürgen,